Hello everyone, Harsh Verma this side, and welcome to a new video in which we are continuing our Network Warrior revision. Actually, it's not a revision of book, but a revision of throughout the concept that this book outlines, and this book particularly focus about the things that we missed in CCNA. So, topic for the day is routing protocols, their types, and their methodologies. So, without any further delay, let's continue to our aspect session over my phone. But first, those who don't know, we are covering this book. This book is called Network Warrior. Everything you need to know that was not on 16 exam by Gary Turnbull. It's a book. This book is quite nice and covers and outlines the most of the things. And I only share the point that I feel like this point need to be told because it's not commonly known. So, example, starting from the definition itself, what's a routing protocol is? A routing protocol is a means whereby devices exchanges the information about the state of network. So every device in which we have a statically defined IP, we need not to do the same for every multiple devices because in some organization there may be hundreds or even sometimes thousands of devices. So sometimes it will be easier if there's something a protocol that automatically shares the routing protocol that we statically defined on a single router and it will be transferred to all other devices as well. So this is what the routing protocol does. The routing protocols are both protocol and application. The protocol themselves sits at layer 3 of the OSI model, while the application that makes the routing decision run at layer 7. So this is the thing that was kind of missing on CCNA, and this for this type of content I'm making this video. Okay. So now using multicast ensures that the only router running the same routing protocol communicate with and discover each other. Basically, it's a comparison why few routing protocols, which earlier used to use broadcast messages in order to communicate, have shifted towards the multicast. So if you learned about the RIP, routing information protocol, must have learned that the routing RIP has two versions: RIP version 1, RIP version 2, and even with support of IPv6, we got the RIP NG, which is called RIP next generation. Okay. So previously the RIP was using broadcast in order to advertise all its advertisement. And we all know that what a broadcast does to a network. It actually slows down because it floods too many packets. And continuing the same, we learned in CCNA that OSPF runs something called processes, and processes are locally significant. But this book tells that OSPF runs different instance, and that instance is called domain. While in EIGRP, the Enhanced Interior Gateway Routing Protocol runs something called autonomous system. We have learned about the autonomous system in the CCNA, which is the different instances of the AI EIGRP. Okay. Finally, normally OSPF is configured on a basis of process ID, which I've just told you. And this is way quite different from the domain that we discussed in the previous line. So OSPF domain and OSPF process ID and OSPF areas are very three distinct concepts and must not be mingled. Okay. Finally, the act of passing route from one processes or routing protocol to another process or route redistribution. We have learned this, and in this book, we will learn in more detail what a route redistribution is, what happens when the redistribution happens, and actually, redistribution is very cleanly explained in the book. So, if I have make the note of that, which I must have. So, this video as well. So the external routes are routing process or redistributed. For example, when we run an EIGRP with autonomous system, suppose XYZ, and if we statically define some routes, then the statically defined route will be an external route to that EIGRP autonomous system. Same is for OSPF domain. It will the static defined route are external to that OSPF process. Next is internal routes are learned within an autonomous system and are more reliable. Okay, we know that the internal routes are the routes that is shared between the EIGRP router. Actually, not the shared between because share will not be the perfect answer to them. For example, we have input that this router has this route to the network, and this book recommend to use this subnet mask or wildcard mask of 000 or a subnet mask of 255, 255, 255, 255 in order to define a route to avoid the networking conflicts. Okay, finally, the external routes are based on the metric which is called administrative distance. We know that what an administrative distance is. If you don't, please watch my previous video. I have told it that it is basically the comparison of the reliability of the different protocols. When we inserting a route into routing information table, we have to know that which protocol or route from which protocol to use. Actually, we have a list of priorities, and the most prioritized is directly connected route, which has an administrative distance of 0, while the second most reliable is the static route, which has an administrative distance of 1. Different protocols have different. Some have 90, some have 200, some have 20, etc. I think OSPF has 110 for as its administrative distance. Finally, the exception for above is BGP, which happens to prefer the external route over internal route. So this line actually tells that for every protocol like RIP, EIGRP, OSPF, the external routes are actually much less reliable than its internal counterpart. But BGP does that opposite, which means that this prefer external route. So external route have a lower administrative value of around 20, and internal routes have a higher administrative value which is of around 200. So it happens to prefer the external route first. Finally, the routing protocol distinguish between different route on the basis of metric. Route with lower metric are more desirable. So metrics are some values which I've already discussed in previous video. It may be of bandwidth, link speed, delay, latency, etc. Or it may be simple as just hop as a metric, which RIP uses. So the routes with lower metrics are more desirable. Suppose to reach a destination, we have two paths. One has around 10 hops and other has only 2 hops. So which route would be more preferred? So as a sane person, you will say that the route with 2 hops will get me the least possible latency, and maybe mostly because sometimes the 2 hops may be a slower interface, but it likely to be lower latency route. So this would be preferred if we are using or talking in context of RIP. Next, calculation of metric is on the routing protocol itself. Some assign its value using hop count, some using bandwidth, while some using reported bandwidth and delay, which I've told you. Nothing, something fancy. Okay, so now we are learning the protocol types. So protocol types is basically the kind of behavior they show. First is distance vector. It only talks about the distance. For example, the RIP, which stands for Routing Information Protocol, talks about the hop distance, and hop distance is its metric. So we can say the protocol types is defined on the basis of the metrics, uh, or the calculation of metric that it's performed, because RIP performs its metric on the hops, so it's a distance vector protocol. Second is link state, which checks the state of the link, speed of the link, and it is done by OSPF, open shortest path first protocol. Okay. And next is the hybrid that takes the both approaches. It also checks for the distance and the link state, the speed, bandwidth calculations, etc. So it will be EIGRP protocol. And finally, the domain that they share. If it concerned with external autonomous system, then it's an external protocol. While if it's concerned within the routes of a internal system, basically autonomous system is the area that is controlled by an entity. So if it's an internal area, the total control that we possess is ours. But if for an external autonomous system, it may be ISP or some other organization that is performing routing, and they may be sharing their routes. So if the routing protocol is concerned with some external autonomous system, then it's an external route, while it is within our internal system, it is called internal protocol. And we do have example. For external, we have EGP and BGP. EGP, which stands for External Gateway Protocol, and BGP stands for Border Gateway Protocol. EGP, I think it's an umbrella term. I do not have a clarification on that. Whether EGP used to be a name of a protocol, it's just simply External Gateway Protocol. By the way, BGP is the internet protocol or the protocol of the generation, because every internet routing happens on BGP. While we have do have a choice to use RIP, EIGRP, OSPF. Uh, and we can say that RIP is still non-existent, because the every system that we have seen in which the routing protocol runs is it's either EIGRP if it's a Cisco device, or it's an OSPF if it's a vendor neutral setup. Okay, next is classful or classless. The distinction between classful and classless, that a classful protocol has provision to include has no provision to include subnet. For example, the RIP version 1 and IGRP, Interior Gateway Routing Protocol. So it's also used to be. Actually, there's also a protocol called IS-IS, which is intermediate interconnection system, or intermediate system. I do have to check that on the internet, but it also used to be an internal protocol. Okay, and actually it's not referred to any classful or classless center, but I just remembered it, that's why I shared it too. Protocol does not have a provision to include the subnet, so it do not supports the variable length subnet masking, VLSM, or the unusual prefix length, for example the 21, 23, 26 types of prefix length, which is not a standard one, which is standards are called /16, /8, /32, this. And finally the classless protocol are those who supports the variable length subnet masking. And talking about the terms of RIP or these kind of protocols, we do have a technique in order to avoid sharing or avoid looping the routes, because looping can happen on layer 3 as well. We know that the STP, the spanning tree protocol, helps to prevent loop in layer 2 scenarios. So we do have some methodologies that prevents loop, just like STP in layer 3, and this is called route poisoning and reverse poisoning. So let's understand this. So the rule of thumb is, when a router learns a route, suppose there's a router 1 or router A that learns something, and then it will pass on that information to router B. Okay, so the router A does not expect is a front facing interface. It learns something from it and pass to router B. So there's a kind of a mindset or a rule of thumb that router A will not must not able to use its exit interface, which is toward the router B, to be used as a backup. So route poisoning helps with that. So route poisoning is a technique in which a distance vector protocol such as RIP, where a router detects a failed or invalid route and immediately advertise it to neighbor with an infinite metric to prevent routing loops and accelerate convergence. So let me tell you first what an infinite metric is. We know that RIP uses its hop as a metric. RIP has a tolerance of up to 15 hops. So as 16 hops to reach, RIP advertises that the route is unreachable. Okay. Suppose a link to a route, for example, the external facing interface of a router that is running RIP has failed. So RIP announces that route with a hop count of 16, which informs other router that this route has now become the unreachable and could not be reached at using router A. And this is all about the route poisoning. The reverse poisoning is little bit catchy to understand and explain. For example, the when router A, which is actually the one who receives the route from external, when shares the route to routing B, sometimes the router A assumes that if I'm not able to access the external facing routes using the external facing interface, it may sometimes try to reach that using the router B connectivity, which of course is not. So router B has to tell router A that I am not the one who has the routes to the external destination. And this scenario is called reverse poisoning. So let me explain it. Reverse poisoning is when route receiving router, which is router B, actually router B was the route receiving router from the router A, and router A was receiving the routes from external, advertise the route back to the source router A with a hop count of 16 unreachable, to make the source router A aware that this router B cannot be used as a backup path to prevent the future loops or to prevent the network loop or layer 3 loops. And if I have to say that you must have to take a single thing from this video, this is the thing. Reverse poisoning. Actually, it took very tries to understand what the reverse poisoning is. There you may find multiple articles telling about different things, multiple YouTube videos. I have been through that, but this is the most accurate definition that I've got. And one more thing that I want to add, that route poisoning, which we discussed earlier, is an event driven reaction. An event of failure. For example, the external link fails. It may be cable fault or port fault. There may be something. Maybe the neighbor router is failed. So it's an event driven reaction. It only occurs when a specific failure is detected. For example, a link goes down due to n number of causes. And the poison reverse is a continuous proactive mechanism. So router B have to tell router A in every update that I am not able to, that I am not the one that will provide you the route to the external network. Okay. Finally, split horizon is a networking technique used in distance vector protocol to prevent the routing loops by ensuring that a router does not advertise a route back to the interface from which it learned the route. This helps maintain efficient and loop-free routing info in network. So reverse poisoning and split horizon is kind of same thing, because router B was learning a route from the router A using the same interface, and it has to advertise a hop count of 16 that it will not be able to, it will not help to able to reach the external thing. So it split horizon kinds of work the same in the background, and yes, it does the same. And the last line for the day is, a network is said to be converged when all its router in the network had received and processed all the updates. So basically, the convergence time is the calculation time of the hop counts, the installation of route in the routing information base. And when this information or this process happens, the CPU gets an idle state, and it only acts whenever something changes. For example, some link failures or some new route installation happens. So it's a interval kind of process. It happens after a particular fixed interval, or it may be situational, or it may be event driven. And that's it for this video. Thank you for watching. Thank you for tuning.